Okay, we have 4-1, day 2. Time to talk about some applications. They're a little bit miscellaneous in the ones we're doing. I shouldn't say that. They're really about sectors, both arc length and area of circles that are essentially formed by angles. For example, on this question right here, here's really what it's getting at. I'm going to draw a diagram. It's not going to be all that good, but, you know, I don't need it to be all that good. What it's getting at here is, here's our initial side. We're staying in degrees because we can visualize those a little easier still. 240 is somewhere down here, right? I'm going to say that that's theta. I don't have the room to say 240, but that's the angle we're talking about. This radius right here is 4 inches. And based on all that, this arc length that the angle creates is right there. We want to know how long that is. Okay, that's what this problem is asking us to do. How long is that? Now I'm going to give you a couple formulas because I want to give you the option to use the one that you want. Because we can take the approach of degrees, or we can go in radians. Absolutely doesn't matter which one you use. The only thing that does matter is that you're in the right units. Okay, but you could do a conversion, so you could always use either one. All right. Now this arc length is called S. All right. Now here's the approach that you have to take with degrees, because I mentioned in class on day 1 and in the lesson on day 1 that degrees have their advantage that they're easier to visualize. But with these formulas that you'll see today, they don't work as well. All right? So for the arc length, we have 2 times pi times radius. You might recognize that as the circumference of a circle. Okay? Well, that means you have the whole circle, which you may not want. So over here, I would say theta over 360, and then just take the chunk of the circle that you want. Okay? This might be the most straightforward way to use, to use this formula. It's a longer, more complicated formula. All right? Now, if we jump down to radians, you're going to consistently see that the formulas are a little bit more user-friendly. Now, we saw that on day 1, that's the definition of an angle in radians. Okay, what is the length of the arc that's formed by the angle divided by the radius? Now, if we just rearrange this a little bit, we get this. I'm just going to multiply both sides by r. You get s by itself, and that would equal r times theta. Quite a bit more simplified than the formula before. Okay, now I do want to show you that we could take the exact same approach and say that s is 2 pi r times theta over 2 pi, right? 360 degrees, 2 pi radians, that's a full circle. Okay, but now with the whole radians thing, look what happens with the 2 pi's, right? And we get here. Much more user-friendly formula. My concern about it is because it's a little bit easier that you always want to use it, and you can't because your angle's got to be in radians if you want to use it. So let's go. I'm going to use the second one. If you want to just plug 240 into the degrees formula, that's totally fine. It'll work. I'm going to use the second one, which means I just need to do a conversion here. It should be 240 pi over 180, which is 4 pi over 3. Okay, now what that did for us is I go to calculate the arc, I can just take r and I can multiply that by 4 pi over 3. to get an exact answer of 16 pi over 3, which would be in inches, because this is an arc length. And there would be my decimal approximation for it. Okay? Again, worth noting, if you had wanted, you could have taken 240 and plugged it in right there. Okay? You've got, in the last example on the area of a sector, I'm going to do the exact opposite. Okay? We have the degree in angles, and I'm going to plug it into the more complicated formula. Okay? But here I switched it to radians and then used the easier one. All right. If we get into linear and angular speed, okay, here's what you really need to know, is that all we're doing is adding the dimension of time. Okay? Linear speed means we have to have some length, some kind of arc length. But we're now going to talk about moving about that arc relative to time. Okay? Now what I'm talking about here is if I'm on the very tip of this second hand on the clock, which we know is 10.2 centimeters, okay, how fast does that point have to be moving around the circle? So I start on the top, right, and I'm going to use the simpler formula, okay? Use that with caution. If I'm just going to go to get my arc length and say r times theta, I've got to be in radians. I have to. Okay? Now, the tip of that second hand, if my math is right here, should go around the clock every 60 seconds. And that's exactly what the second hand should be doing. 1 trip per minute. Okay? That's really all I'm doing now is adding this element of time. That's how fast, that's how much time should go by for it to move all the way around this particular arc, which is an entire circle. That leads me to theta, okay? Because r, it tells us in the problem, is 10.2, but to use this formula, I need an angle, okay? And it's talking about 1 revolution all the way around the circle, so it's 2 pi, okay? And again, to use that simplified formula of r times theta, I've got to be in radians, okay? Now I would just simplify this, and what you'll end up getting is about 1.068, and my units were centimeters per second. That's how fast, for a clock that size, that's how fast the tip of that second hand has to be moving. Okay? Now, down in part, I'm switching context to this Ferris wheel. I want to add one more formula here, because the first part is going to get into angular speed. That is not based on an arc length. That is just the angle over time. So the units here, okay, like if you think about this Ferris wheel and you're starting in this initial position, as you keep moving, the angle you form with the center just keeps changing. All right? Angular speed is how fast, in terms of like radians per second or degrees per second, how fast is that angle changing? All right? Now this says that the Ferris wheel goes all the way around in a minute, so that's going to be on the bottom because that's my time. All right? What I want you to notice here in this angular speed calculation, the number 50 for the radius is not going to come up. Okay, for angular speed, it's not based on how big the circle is. Linear speed does, because there you were talking about an arc length, which we'll get to for this problem in part B. So all I really have to have is what's my angle. Okay, what is my angle? I'm going 1.5 revolutions. All right? And for the next part, for the easier calculation for linear speed, I want to be in radians. So on the top, I just need to put 3 pi. And then I'm going to say that that angle is changing 3 pi radians per minute. Okay? That's how fast, as that angle changes relative to the initial position, that's how fast it's changing. 3 pi radians a minute. Now the reason I chose to be in radians is thinking down below here as I'm going back to linear speed. This is still going to be per minute. But now I got to get switched over to feet. Okay, I've got the angle of 3 pi. I want to use the simplified version of the formula, or I shouldn't say the simplified, the easier version, which is why I'm in radians. Okay, but I've got theta, and obviously I've got time here as a minute. But now as soon as I make the jump to linear speed, I need to know how big of a circle we have. Okay, I need to know how big is this arc. Well, this arc is formed by a circle that has a radius of 50. Okay, so I could go 150 pi feet per minute. That's an exact answer. Difficult to visualize. If we took the decimal approximation from a calculator, we'd have 471.24 approximately feet per minute. Okay, angular and linear speed both add the element of time. Okay, but for linear speed, you're dealing with an arc length, so you're going to use your radius. Okay, that's why I switched it back to the units of feet. Angular speed, no radius. All right, this one is going to be pretty similar to the first one we did. I've got 2 formulas to show you. Again, I'll split it up and we'll do formulas on the left and we'll actually solve the problem over on the right. Now it's the area formed by a sector. Okay, this would be your arc length, and before we calculated that, now we want to know, we got a radius of 70 and a 120 degree angle. What is the area of that particular sector? Same situation. 2 formulas, one for degrees, one for radians. And the degrees ends up being really similar, that now this first part is just the area of a whole circle. Pi times radius squared, you've probably seen that, who knows how many times over the years. That's a whole circle. Right, then what we need to multiply that by is what fraction of a circle do we have? Well, that's going to be formed by the angle. We're going to use that formula. Now I'm going to give you one little hint on this one that you're going to see come back up later. What we're essentially doing in this problem is we're calculating the area of 1/3 of a circle that has a radius of 70. Okay, now as you look at those numbers, see if you can see where 1/3 eventually comes up. The structure for the radian formula is virtually identical, but again over here, if our angle is in radians, it should be relative to 2 pi. Now we see this happen once again, cancels out with the pi's, and we have 1/2 r squared times theta. Okay, so the radian formula once again gives you a little bit of a simplified version. Okay, it works better with these formulas. All right. Now, last time when I was doing the arc length formula, we converted it to radians to use the easier formula. Let's do the opposite. It had degrees. Let's just stay in degrees. So I would have pi times 70 squared. That is the area of a circle that has a radius of 70 feet. But our sprinkler doesn't rotate all the way around. It only rotates 120 degrees. Okay. Now, I'd mentioned earlier this is really going to be based off of 1/3 of a circle. Notice, and you don't need to show this step, right? I'm just trying to kind of give you some intuition about the formula as to how it works. That reduces to 1/3. So what we really have is 1/3 of a circle. That would all need to go into a calculator, and you would get the decimal approximation of 5,131.27. And this is now an area calculation, so we should be looking at feet squared.